Hi all, welcome to another video of Turing Nexus. In this video, I want to bring attention to this paper, Alan Turing's paper on computable number with an application to the n-shadings problem. I'm not sure if I'm pronouncing it correctly, but yeah. In a simple term, it is referred to as decision problem. This will not just be a paper review, it will be more than that. Why do I say this? Because I will bring for the review just as it is for you, and also we'll discuss about the major events which gives a different perspective to this whole paper. This paper to date is one of the most important literature. This paper has made waves when the field of computer theory was developed, and modern day digital computer architectures were relied on this. The title of the video is little bit not directly related when I mention the Turing's paper, Little Boy, and the von Neumann architecture. Yes, I'll try to bring in the missing parts. So yeah, so just paper, if we look at it, just a review just as it is. In this paper, Alan provides a theoretical conception of a compute machine with possible configuration. Why was it important at that time was the different great minds at that time were discussing about the feasibility of what is possible with a computer and what is not. See, before this paper, the computing devices were there, but it was just a calculator, a massive calculator. IBM was the in the forefront. They were supplying uh, enhanced calculators, and their idea is to man force were behind. Several workers were assigned to number crunching activities. Their job is to just multiply, add, and perform all the things which our single calculator used to perform. And this used to happen across a big room. So actually, humans were used. The irony today is the programmers who are creating the software will be replaced by AI. In the same way, that time, all the great minds who were very good at crunching numbers, who were very good at multiplying, adding, subtracting, all those mathematical forms, they were replaced by these computing devices, calculating devices to be precise. So Alan brings in the uh, conception theory-wise about a computing device, computing machine with configuration. He also introduces the idea about circle and circle free. This is based on the symbol which the compute device produced. Uh, Method to make a machine compute with 1 0. This was important because this paper is described the machine as an application to n-shadings problem, which we will discuss more in detail. But before to that, the paper as it is just gives us the mechanical aspects and also the relationship of brings the relationships of mechanics and logics, such as read, write, erase, these actions being performed by a header. This paper, there is a theory where most of them say this machine which Alan Turing is talking about is based out of a typewriter. He was having a typewriter, and that was an inspiration. In this paper, he visualizes a infinite tape which acts as a memory storage unit and a header which have access to this infinite tape, and the header moves left, right, and across the tape, performing the calculations. And this machine is able to read, write, erase, even though uh, it's it's just an abstract machine. I am not sure if there was any realization of such a header which will be able to do read, write, erase kind of activity. But yeah, just look at the ambition and how ambitious Alan is right here. I mean, Realizing is one thing, but this much vision, but till date we are able to do all these things using our computer, thanks to them. And also he goes on to talk about his most part of the paper. He talks about now he has laid down the fundamentals of what a machine is, what it is generating symbols, and what are the characteristics. Then he talks about the configurations, transition. So in a simple term, it's a state machine. Different states were defined, and depending on the input type of input, the state transition has to take place. And this was in the skeleton table. Yeah. And also he introduces the concept of universal machine concept and capabilities. This is a very important aspect where he talks about the feasibility of making use of this machine with any mathematical formula and able to implement algorithms. At that time, algorithm was not just pseudocode, which we are doing right now. Algorithm included even the mechanical implementation, mechanical realization of how the program will be done. So that's it. I mean, the paper review, just as it is, talks length and breadth about these machines, symbols, kinds of symbols, concept, logics, read, write, erase, universal machine. Yeah. Now, when you focus on this n shadings problem, that's when you get to know a lot of things. So this n shadings problem is about, proposed by David Hilbert. He asks whether there exists a definitive algorithm to determine the truth or falsehood of any mathematical statement expressed in formal logic. Let me give an example. This example which I'm giving you right now is from a TED Talk video. I'll try to provide the link to that. What actually it means is that suppose I give a statement. This statement is false. That's the sentence. That's the sentence. This statement is false. Now, to think about it, is the sentence on its own, is it true or false? If I say it's true, then this statement is false. It is false. But when I say it is false, then this statement is false becomes true, right? Yes. So if you go deep to this, it will turn it out as a paradox problem. So that's what Hilbert is trying to explain here. There were so many mathematical concepts, so many mathematical formulas, which were very accurate. When you talk about it, when you formulate it, it's very accurate. But the proof was little bit contradictory when you try to prove that. It was unable to. We were unable to do that. So that's when the in shadings decision problem came to discussion. Several, all the mathematics were there were actually at that time when he posed this problem. All the learned, great minds, they separated themselves in two groups. One who opposed whatever he said. One group said this is not at all required. He is just making this up. This is unnecessary. Nobody should read this. We shouldn't waste time in this. But there was another group which was like supporting his questions, telling this is a legitimate question and this needs to be discussed and this needs to be looked into. So then came what then based on this, the objective was proposed, that is a mechanical procedure algorithm. Yeah, as I said, at that time, even mechanical procedure was inclusive of algorithm. Right now, algorithm is kind of a pseudocode that we all enjoy. No need to worry about the other things. We enjoy different, we have the liberty to choose a programming language, type of database, SQL, no SQL. The options are plethora. At the time, it wasn't. Also, to understand this paper, um, when I read it first, it was very difficult for me to process. But then I had to tell myself that this paper is actually simple to comprehend if I open to the information which flows. It's just as it mentions. Uh, Alan talks about a header moving left and right. That's it. There is no more uh, focus or attention needed. That's what. To him, to Alan at that time, thinking about that much itself, bringing the notion of a header moving left and right, reading, writing, erasing, is uh, groundbreaking. Actually, yes. Right now, for us, it is simple. We have seen the hard disk, we have seen the SPTs, we have seen the solid state drive. So, yeah. So, what is the significance? This enshading sedation problem represented the foundation question in mathematics and computation regarding the limits of computation in formal systems. Later, Alan Turing and Alonso proved in 1930. When was this paper? And in 1930, we have the proof, such as universal algorithm exists, showing Einstein's problem is undecidable. And there was a huge impact. The concept of undecidability was brought into picture. That's when the groundwork for modern computer science was discovered. Also, the famous field of computer science that is not even computer science, it's a different field, computability theory, computer theory. The computer theory is not about, data structures and algorithms. I looked into it. I saw the introductory class from MIT, uh, and I found out that it's not about the algorithms or data structures or efficient programming. No, it's about, the limits of computer or what problems are solvable by computer and how efficiently it can be done and what are the limits. One famous limit is the halting problem. The halting problem, as the name suggests, the computer enters into a halt state or infinite loop. So if we have a mind map, right? The key contribution to this enshadings problem came from Alan Church and Alan Turing. And the field included lambda calculus, just Turing thesis, proved undecidability, developed the Turing machine. Turing machine came into picture and Turing test was also present. What was the impact? Um the impact were the foundations of computability theory, relation to the halting problem. That's a really great impact, and connection to modern algorithms. And in the modern implications as well, applications in logics and AI were derived from this. And cryptography is another area of deep area. Given this many information, it just while doing this research or while studying uh, different connecting dots, it was like as if I was sewing I was stitching a piece of cloth which was initially torn here and there, but still I was not able to stitch it completely. I felt like, okay, fine. It seems like, I am still missing something. So I this was about the events which happened before and after, very nearby. And to make myself to have a peace with this paper or with this implementation, I had to look into the real time is a very frequent, very near course of actions which has happened, how computer came into existence and how things happen. In order to do that, I have extensively covered a lot of resources. I have watched so many YouTube videos. I have I have read so many other articles on the internet. There were so many things, but out of all this, one thing is kind of gave me the enlightenment. You can say, yeah, enlightenment about the, reach that this one paper, Alan Turing's paper, had. Yeah, that's this evolution of computing in Manhattan Project. If you look at the milestone, things become very clear. I mean, this is really interesting. So what I have done here is I have captured the timeline and I have um, mentioned the series of events putting across evolution of computing in the Manhattan Project. So early foundations 1936 and 1939. 1936 Alan Turing's paper The Turing Machine, and 1939 Einstein's letter to Roosevelt. So if you have watched that Oppenheimer movie, you would understand that this Einstein writing a paper was captured there. And the theoretical advances. It's very interesting to see all the events happening hand in hand. It's like, uh, this was meant to happen and that was meant to happen. And there is a perfect combination. Theoretical advances are like Turing introduced the concept of universal machine, 1941. The first programmable electronic computer became operational. And in 1942 and 1943 and even 1945, wartime development happened on the go. And John von Neumann was included in the Manhattan Project to make the computation, that is the number crunching, easy. He made the calculations very easy, and IBM provided the famous Mark I machine, which is uh, not a computer but a perfect calculator, which can reduce the manpower and increase the accuracy of calculation and save time. So John von Neumann then um, actually he says this. If I can show it to you. Okay, there is a yeah, yeah. This one, actually, this is really something great. This I'm thinking about something much more important than bombs. I'm thinking about computers. This in itself stands and talks for itself, right? That was all possible. He understood the breakthroughs possible by normal computers and his short-handedness of not able to perform some of the actions. And he went across the historical papers and he found the universal machine concept from Alan Turing. And then he, by the time the Trinity test was conducted, he was ready with that system. Uh, and all the mechanical dials, tubes, punch cards, whatever was available at his disposal, he was ready with an architecture. The architecture was nothing more of a, it talks about a memory unit able to read, write, and able to perform logical operation. And then making use of that, the first hydrogen bomb calculations were done. And then in 1946, Manhattan Project ends and Atomic Energy Commission was formed. It's really interesting to connect the pieces of historical events and see how a mere paper travels to and then gives rise to a great architecture, John von Neumann's architecture. That's when I thought, while naming this video session, what should be the apt? That's what Turing plus little boy John von Neumann architecture. So what is a takeaway? I mean, there is a subtle an undeniable matter present here throughout this course of action, and it is uh, really interesting to me because it have given me a lot of things to think about. So it's been proven that whatever modern advancement which we are able to see and enjoy to date are nothing but uh, mathematics, pure mathematics. So many things are there, so many mathematical concepts, theorems, axioms, and the paradoxes like undecidability. It just, when we go very close and try to realize it, that's when we are able to create advancement in modern technology. So what I think would happen is we would be doing great things which will look like magic, but then on the bottom, it will all be driven heavily using maths, formulas, axioms, principles. That's why it's very evident. And as I grow, as I keep thinking about these things, it's really I bear witness to the greatness of mathematics. Yeah, this now after going through all these things, it whenever I sit and go come across any mathematical concept, it will not be the same. This the seriousness and the way I will approach the mathematical topics would be different now. So one should always keep in touch with their roots, that is maths, and always keep practicing. That's what I will do, and I'll try to practice as much as possible and see where that leads. Hope you guys enjoyed, and I'll try to discuss more on the John von Neumann architecture. But my my target here is to cover as much of papers related to computational theory, computer field, so that I will be able to cover the theory required till AI and advancement. Yeah, I want to cover length and breadth as much as possible and do great things in this field of AI. Thank you. Hope you guys enjoyed.